Hello. In this video we're going to be looking at Newton's law of gravitation, which can be represented by the formula shown here. Newton's law of universal gravitation states that every body in the universe attracts every other body with a force that is directly proportional to the product of their masses, m1 multiplied by m2, and inversely proportional to the square of their distance apart. Now, we're not going to look at this in too much detail, but we are going to focus on the second part, the inverse square nature of the law. Now you can see the part in orange. That's the bit we're going to be focusing on. And it's called the inverse square law because it's the inverse, see it's below the line, and the square law because the variable, in this case the distance apart represented by r, is squared. So what does this mean for astronomical objects? Well, let's take this comet with its elliptical orbit around the Sun. Due to the fact that it has an elliptical orbit, it won't always be the same distance from the Sun. Sometimes it's going to be close, like at this point here. In fact, at this point, it's closest in its orbit to the Sun, and we call this point perihelion. And at other points it's going to be further away, and the point where it's furthest, this point, is called aphelion. Now you might have guessed it, this links to Newton's laws of gravitation. The amount of gravity experienced by the comet is going to be different at these points. But how different? Well, let's just imagine that at perihelion it is x astronomical units from the Sun. And at aphelion, it's 20 times that distance away. It would be easy to think that at perihelion, the force of gravity would be 20 times larger than at aphelion, as it's 20 times closer. But you'd be wrong. Remember, it's the inverse square law. We have to square that difference. So in fact, at perihelion, the force of gravity would be 20 squared times bigger, which is 400 times larger. Let's have a look at another example with some numbers thrown in. Here, our comet is 4 astronomical units away at perihelion and 16 at aphelion. So firstly, we need to work out how many times closer is it when it's at perihelion. So we'll divide 16 by 4, which shows that it is 4 times closer. Therefore, the gravitational force when it's at perihelion isn't 4 times larger, it's 4 squared times larger, and so it's 16 times greater. We can also use Newton's law of gravitation in other examples. Here, a fragment of a comet is on a collision course with Jupiter. When the fragment is 0.065 astronomical units away, the pull of gravity that it experiences from Jupiter is 80 units. We want to find out how that force changes when the fragment gets closer and is only 0.01 astronomical units away. Well, we can use the same method. Firstly, we need to find out how many times closer it is when it's nearer to Jupiter. And so we would divide 0.065 by 0.01, which gives us 6.5. This means that it's now 6.5 times closer, but remember, the force of gravity experienced isn't 6.5 times larger, it's 6.5 squared times larger, which is 42.25 times greater. So if the original force was originally 80 units, and it's now increased by 42.25 times, we can just multiply those two numbers together, which gives us a force of 3,380. This means that the force of gravity experienced by the fragment when it is 0.01 astronomical units away is 3,380 units. So now that you are confident at using Newton's laws of gravitation, have a go at our key questions.